Good morning, chemistry students. Here is your last set of notes for this COVID-19 situation over Chapter 9, Section 2, the portion about other stoichiometric calculations. So, again, as we kind of get ready for this, remember that it will be helpful to have your periodic table out. It will be helpful for you to have your chemistry toolkit out. It'll be helpful for you potentially to have your helper sheet out with polyatomic ions and such, okay? So we've been talking about stoichiometry, and stoichiometry is so important because pretty much any time you do a lab, you're going to do stoichiometric calculations. So far, we talked about, you've done mole calculations, okay? And you've done some mass, and even a mass volume one. There are many different types of problems here, okay? There are those kind of first ones we talked about, which was that mole. Again, that means you're given an amount in moles and you're asked to calculate an amount in moles. Again, to do those, you just need to use a mole ratio. You may be given a mass problem. Again, idea here is that you're given something in grams or kilograms, and you're asked to calculate a different substance in grams or kilograms. Again, when you've done these, you should have noticed that you've needed to use a total of 3 conversion factors. You've used molar mass, a mole ratio, and molar mass again. You could be asked to do a mass volume problem. Again, idea here is that you're given something in grams or kilograms and asked to calculate the volume. Typically, you're going to be asked to calculate the volume in liters, and usually they're going to stipulate STP. Again, typically this is going to require a total of 3 conversion factors, right? You're going to start with a molar mass conversion factor to convert to moles, a mole ratio to convert from one substance to another, and then molar volume to convert it back to volume. You may also be asked to do a particle mass problem. Again, that would mean that they've given you a certain number of representative particles and they ask you to calculate the mass. Or remember, with any of these, we could kind of go the other way, right? You might be given a mass in grams or kilograms and they ask to calculate the number of representative particles of the substance. Again, this is one that's going to involve at least 3 conversion factors because, again, you're going to convert your particles to moles using Avogadro's number. You're going to use a mole ratio and then you're going to use a molar mass. The key to doing any of these problems is that you must choose which conversion factor and I'm going to put an S on it because sometimes it's going to be more than one to use. That's why sometimes it's very helpful when you're doing these problems to have your chemistry toolkit sitting there, because looking at your toolkit, it gives you your choices of what you can convert moles to. Remember that the only way to go or to convert from one substance to another is using a mole ratio from a balanced chemical equation. And most of these stoichiometric problems, you are going to be asked to go from one substance to another. So typically, if you're doing a problem and you don't have a mole ratio in there, likelihood is you've done it incorrectly. And again, remember, the requirement to get a mole ratio is you have to have that balanced chemical equation. So just kind of really quickly, again, reviewing what you have on that chemistry toolkit, right? You have those count ones, which are 6.022 times 10 to the 23rd formula units for 1 mole of ionic compound. You have the other count, you have a total of 3 count ones, remember, because you have 3 different kinds of substances. So you can have Avogadro's number of molecules to 1 mole of molecular compound. And our last count one is 6.022 times 10 to the 23rd atoms for 1 mole of element. Right? Again, remember we kind of have 3 different ways that we can measure matter, right? We can count it, we can take its mass or weight, okay, and we can measure its volume. And we can use the mole for all of these. So these are our 3 that involve the mole for counting. For mass or weight, remember that one has a special name, okay, that's molar mass. And it's some number of grams of substance over 1 mole of substance. And again, that substance part is important there because remember it has to be the same substance. I can't change from like oxygen to hydrogen here. If this is oxygen, this has to be oxygen, okay? So those substances have to stay the same. Remember, we get this number from our periodic table, right? We add up our average atomic masses from our periodic table to get our number for molar mass. Remember, you don't have to show work for how you get your molar mass, but you do have to show your molar mass when you're doing problems with conversion factors. Okay, so that's our mass, weight. Okay, lastly, we have volume. Okay, and remember again, that one has its own name. It's molar volume. Okay, and it's 22.4 liters of gas over 1 mole of gas. And remember, this one has to be at STP, that's standard temperature and pressure. Again, important idea here is, again, this is the same gas both places, so I can't have oxygen in one spot and hydrogen in the other. That would be wrong. It has to be oxygen and oxygen. Okay, and standard temperature and pressure again, 0 degrees Celsius, 101.3 kilopascals, or 1 atmosphere of pressure. Okay, remember these are our conversion factors that you learned in Chapter 7. The only new conversion factor that you learned in this stoichiometric chapter is the mole ratio. Okay, and that is some number of moles of, and we just kind of put A over some number of moles of B. Okay, and again, this A, this B, that's important because those are different substances. Remember, this is our only way to change from one substance to another is a mole ratio. These numbers here, remember these are our coefficients in our balanced chemical equation. So that's why it's very important that you are able to correctly write and balance a chemical equation because you have to use those coefficients in your mole ratio. So using these 6 conversion factors, you can do all these different kinds of stoichiometric problems. Okay, so again, hopefully you've made yourself a little chemistry toolkit, a little piece of paper or an index card that has these tools on it. So we're going to take a look at an example. Our example is that ammonia reacts with oxygen to produce nitrogen monoxide and water. How many liters of nitrogen monoxide are produced when 1.40 liters of oxygen reacts with ammonia? Okay. So, again, the first thing that you should notice here that we don't have is that balanced chemical equation. So again, I'd encourage you to pause the video for a few minutes while you work to write and balance that chemical equation. So again, here we have ammonia, so that's a reactant. Reacts with oxygen. Oxygen, remember, is O2 because it's part of Hofbrinkel or Brinkelhoff to produce nitrogen monoxide. That's a molecular compound. Prefixes become subscripts. So this is just NO. And water, you know, is H2O. So that's my skeleton equation. So when I start to go to balance this, hopefully you notice right away I have 3 hydrogens and 2 hydrogens, which means I'm going to have to make them 6. So I'm going to put a coefficient of 2 and a coefficient of 3. Okay, so now I have 2 nitrogens, so I need a coefficient of 2 on nitrogen monoxide. So now I'm ready to deal with oxygen. And remember, oftentimes I want to leave oxygen until the end because it's oftentimes the most difficult one. So right now I have 2 oxygens here and 3 here, which is 5. And that's a problem because I can't get 5 here. Okay, but again, we could kind of use that little trick, right, where I need 5 over 2. But remember, I can't have 5 over 2, okay? So I have to, okay, get rid of that 2. And the way I'm going to get rid of that 2 is I'm going to double everything. So my coefficient of 2 here is going to become a 4. My coefficient of 5 halves is going to become 5. My coefficient of 2 here is going to become 4. My coefficient of 3 here is going to become 6. Now, let's see if that works, right? So we want to check always. So we have 4 nitrogens and 4 nitrogens. 4 times 3, that makes 12 hydrogens. 6 times 2, that makes 12 hydrogens. 5 times 2, that's 10 oxygens. I have 4 oxygens here and 6 here, which makes 10. So this is correctly balanced. So now we're ready to look at our problem, which was how many liters of nitrogen monoxide. So again, I'm just going to put, oops, I'm not going to use that though. I'm going to put question mark liters under nitrogen monoxide are produced when 1.40 of oxygen reacts with ammonia. Okay, so this problem is asking me, this would be a volume problem, and this problem is asking me to convert 1.40 liters of oxygen into liters of nitrogen monoxide. Again, I start the way I always do. So I'm going to start with 1.40 liters of oxygen. Again, my only way to change from one substance to another is a mole ratio, so I know I'm going to use molar volume to convert liters of oxygen to moles of oxygen. Moles of oxygen will have to go in the denominator. So, and again, I'm trying to change to nitrogen monoxide, so moles of nitrogen monoxide are going to go in the numerator. But I don't want moles of nitrogen monoxide, I want liters. So moles of nitrogen monoxide is going to go on the bottom. Liters of nitrogen monoxide is going to go on the top. And now I'm in liters of nitrogen monoxide, so I know I have this set up correctly. Now I want to come back and fill in my units. Remember, this is my molar volume. And although this one didn't stipulate STP, we can just assume it is. This is also a molar volume conversion factor, and this is my mole ratio. Okay, so molar volume, if you're not sure, look at your chemistry toolkit. In front of moles is 1, and in front of liters is 22.4. Mole ratio, again, we get our numbers for our mole ratio from our coefficients of our balanced equation. So in front of moles of nitrogen monoxide, I'm going to put a 4 because that's my coefficient. And in front of moles of oxygen, I'm going to put a 5 because that's my coefficient. All right, again, we're back to molar volume. So the number in molar volume that goes in front of liters is 22.4. And in front of moles is 1. Now, this is one where you do want to be kind of smart about putting it in your calculator because you all have had algebra before. And so you know, right, that it would be kind of silly I have 22.4 here and I have 22.4 here. Now, I need to have it written in my conversion factors. But when I put this in my calculator, right, those are just going to cancel out. So it would be kind of silly to put those in my calculator, okay, when I do this. Okay, so again, remember you have to multiply by numbers in the numerator and divide by numbers in the denominator. And again, we want to have three significant figures because 1.40 has three significant figures. So my calculator gave me oops, not what I meant to use, 1.12 liters of nitrogen monoxide. It's really important that we have those units on there. Okay, so you'll notice on your outline there's a second example. It is how many molecules of ammonia are needed to react with 1.40 liters of oxygen. So again, I'm going to put my 1.40 liters underneath my oxygen. And it's asking how many molecules of ammonia are needed. So this would be a volume particle problem. Again, I still approach it the same way. I'm still going to start with my given, which in this case was, okay, the 1.40 liters of oxygen. Again, I have to change from one substance to another, so I know I'm going to have to use a mole ratio. So I'm going to use molar volume to convert liters of oxygen to moles. Moles of oxygen will have to go in the denominator. And so moles of ammonia this time are going to go in my numerator because I'm being asked about something with ammonia. I can't stop in moles because we want molecules. So moles of ammonia will go on the bottom. And I have a tool that has moles and molecules in it. And to use it, my substance has to be a molecular compound, which this is. So I can use that tool to convert it to molecules. So I know I'm in the right units now. What about my numbers? Okay, again, this first tool here, right, this is molar volume. And so in front of moles is 1 and in front of liters is 22.4. This next tool, right, this is my mole ratio. This is how I'm changing from one substance to another. To get my numbers for my mole ratio, it's my coefficients for my balanced equation. So I have a coefficient of 4 in front of ammonia and a coefficient of 5 in front of oxygen. Now, this is one of my count conversion factors. Okay, so the easy number is moles, it's 1, and this is where that Avogadro's number comes in. Again, I have some numbers to multiply by, I have some numbers to divide by, okay, so, and hopefully you have figured out how to put scientific notation in your calculator. And again, I want to have three significant figures. So I get 3.01 times 10 to the 22nd molecules of ammonia. Okay, again, because this one's maybe a little bit more difficult to put in your calculator because there's that scientific notation, right? The way I put this in my calculator is 1.40 times 4 times 6.022, that E button 23, divided by, I have to have parentheses because I have two things here in the bottom. Okay. And if you do that, you should get the correct answer. So it's your last homework assignment. Can you believe it? It's finally almost summer break. Although this has seemed like a crazy long, weird end of the school year after having nearly a month off and then back to school for 6 weeks. But your last homework assignment is on page 250, number 22. Again, I will make a video key and a handwritten key for you about how to do this in case you're struggling. Have a good day. Talk to you tomorrow.